Okay, so in this video, we're actually going to start talking about the gradient projection algorithm, which is a really important algorithm for solving these constrained convex optimization problems that we've been talking about. So let me share the slides. So we're going to get into the maths, we're going to get into the algorithm for this. And it'll, there's a lot of theorems, there's a lot of theory about this that can make it seem complicated, but I really want to give you the picture of how this algorithm works, because it's actually kind of intuitive, and you'll get the picture of what's going on with a few nice illustrations. So just to remind you, here's the problem that we're trying to solve. So we have a convex continuously differentiable function. We're trying to minimize that subject to some inequality constraints, and we're going to restrict ourselves to just linear inequality constraints here. So what does this look like? So here's the visual, the mental image that I want you to have of this problem. So here's my cost function in the colors here, and the minimizer, the true minimum is going to be where the color's densest up in the top right here. So that's the problem we're trying to solve, and as an unconstrained problem, you know how to do that. You could use conjugate gradient, steepest descent, any of these different variants that we've been talking about, to start somewhere and head towards the minimizer up in the top right. But we don't have an unconstrained problem. We've got a constrained optimization problem. So here's 4 constraints, and we'll make them inequality constraints such that the feasible region here, the region that we want to find the minimizer over, is this green trapezoidal area. So the important thing to say is that there's 8 constraints. There's 8 things to check here, right? So we could write down the KKT constraints. We could do constrained optimization. We could do a Lagrange multiplier problem to look for a minimizer in the center of this region, and then all of the 4 boundaries, then all of the 4 corners, which gives us 8 things to check for where the minimizer subject to the constrained problem is. There's actually even more problems. If we use the KKT conditions, we have to check that things like constraints, you find the minimizer when constraints 1, 2, and 3 are active, for example, which can't happen, and you figure that out from KKT. But if we were going to check this algorithmically, just using the Kruskal-Tucker conditions, there's all these different things we have to check. Right, so it becomes a really computationally expensive problem. So what we need is an algorithm where, given a starting point that's in this feasible region, so given some guess at the solution, we want to try and navigate to what the constrained minimizer is, and that's what gradient projection does. So let's start at this. Guess at the solution x0, somewhere in the feasible green region there. And then what we want to do is we want to try and improve that guess, right? We want to take a step towards the minimizer of this function. So what's a sensible direction in which to step? Well, you could throw away all these constraints and just think about the unconstrained minimization problem. And you can imagine taking the steepest descent direction, in the direction it's heading directly towards the true minimizer up here in the top right. And that's actually what gradient projection does, right? So the very first thing that we'll do, that the algorithm does, is it steps in that direction, heads downhill in the steepest direction that I can towards the minimizer, and it takes a step in that direction. Eventually, because this is a constrained optimization problem, we're going to hit the boundary. Right, we're going to hit the boundary of where of our feasible region, and we have to stop there. So the first step of gradient projection is generally going to be in the direction of the global minimum of this surface, but sending us in one step towards hitting the boundary and saying we can't go any further. Now, what's the next thing to do? So now that we're on this constraint surface, we want to keep heading downhill. We want to keep generally heading in this, up towards the top right of the screen picture, towards the global minimizer, but we are stuck to we're constrained to our feasible region here. So what's the direction the gradient projection is going to take us in? It's going to have to move us along the boundary here, right? So we want to stay on this constraint. So we have the active constraint, of G2 here, right? The second constraint is active because we're on this boundary here. And we're going to stay on that active constraint, and we're going to still head downhill. And that's going to take us along the constraint G2 equals 0 to the corner of this feasible region, right? The lowest point along that curve is going to be in the corner where you now have G2 equals 0 and G3 equals 0, right? G2 equals 0 and G3 equals 0 along this line. So the second and the third constraints are active, and you're going to get stuck at that point there. You can't go any further because you become a non-feasible point. So that's the second step that gradient projection takes. And now, if you imagine level curves for this surface here, you can probably imagine that we can do slightly better. We can still head slightly downhill on this overall cost surface if we move along constraint 3. So you can probably imagine that there might be a slightly better point that's a minimizer along the constraint G3 equals 0 along this straight line, and it is, we're looking for a point where the level curve is going to be just tangent to the line G3 equals 0, and that's what gradient projection does, right? So we can't go do any better when constraints 2 and 3 are active, but we can do a little bit better. We can get a little bit lower if we head along G3. So we now solve that constraint minimization problem. So we have to relax the constraint of being on G2 equals 0, being on this line, the second constraint, and we relax that. We move along the other direction that's available to us along G3 until we get to the minimizer, which is going to be around about here. And then gradient projection is going to terminate, and that should be the minimizer at x3 there, subject to these constraints. That's it. That's the gradient projection algorithm. We'll talk it through, to prove to sort of prove mathematically why every step here works, and to write down the algorithm. There's some more mathematics to write, right? There's a lot more for us to say at a sort of technical level, but that is the picture. That's all the algorithm is. If you understand that idea of moving around the boundaries, then you've got the gradient projection algorithm. It's kind of all you need to know to understand how this algorithm works. If it seems like the simplex algorithm, right, if this reminds you of the simplex algorithm for people who've done that before, there's a good reason for that, right? It's very, very similar to the simplex algorithm. And when you look at the pictures, it's actually one of the more sort of intuitive algorithms that we've talked about in this course. I want you to keep that picture in mind, and we'll delve into presenting the algorithm formally, and then building it up, talking about the mathematics behind it, and making this all a bit more formal. But that's the picture. Okay, so how does this work? Well, it all comes back to this idea of orthogonal projection, which we talked about in a previous video. And the idea generally is that we're always trying to move in the direction of steepest descent, so in the direction of negative gradient f of x is our overall cost landscape, but we want to get constrained to the set of our active constraints, right? So we want to stay on the green set, and so instead of moving in the direction of the blue arrow, we project that onto our set S, and we move in that direction. So we really want to write negative gradient f of x as u plus w, right? And there's a couple of things that can happen here. So if u is equal to 0, right? So if negative gradient f of x points directly out of the page, right, up from this green surface here, and the gradient f of x is orthogonal to those constraints, and there's no descent direction that I can take that's within my active constraint set S. So that's a special thing. We're going to talk about that over the next few videos. But if that's not the case, if u is not equal to 0, then I can move. I can create this set of directions that are orthogonal, that add up to negative gradient, the steepest descent direction, and use a feasible descent direction. So with that in mind, here is the outline of the gradient projection algorithm. So this is incomplete because there's a few things that we don't flesh out fully in this just yet. So for starters, looking at this, here's the idea. We take a feasible starting point, so a point that's within our convex feasible set, and then we iterate a bunch of times. We descend in some direction, and essentially we take the best step that we can in some direction, such that we stay within our feasible set. That's this line here, and then we update. We keep moving around. So there's a few messy things here. For starters, the 99 there, obviously there's nothing special about running this algorithm 99 times. That's just a big number. So we want to have some more, eventually we'll want to have some more sophisticated way of figuring out when to terminate. The big thing that's missing here that we'll talk about in future videos is what the something special is that you do if you can't find a feasible direction to step out. Let's park that for the moment, and we'll come back to that problem later on. But for now, the thing that we need to do here to actually run this algorithm is to calculate this descent direction. And you can see to create this descent direction U, I need a particular matrix called PS here. And so the big question is, what is that PS? How do I come up with it? Yeah, and so the answer comes back to this idea of orthogonal projection. So when I showed you this slide in a previous video, I presented a couple of theorems that actually tell you how you can construct these orthogonal projections, how you can find these U's that are orthogonal how you can construct these U's that are orthogonal to these W's and that create this orthogonal projection here. To summarize what the content of those slides, here's what you do, right? So there's linear algebra. So this is this is a piece of linear algebra that technically uses techniques that you learned in Maths 1A or 1B. And there are theorems that prove why all of this work that are standard sort of linear algebra theorems. I won't go through them. I'll leave you to read the theorems, but here is the procedure. So the idea is that we're on the boundary of our feasible region. Imagining that we're on the boundary of our feasible region. So we have some set of active constraints, right? So I of x like that. And then what we do is we calculate the gradients. We compute the gradients of the constraints, those active constraints. They're going to be just vectors because these G's here, our constraints are always going to be linear constraints. Those gradients will just be vectors with numbers in them. And we can stack all of those vectors into a matrix that we call M. Right? So once we take all these gradients, we get a bunch of vectors with numbers, we shove those into a matrix, so put them all in as rows of a matrix M, and then we find this thing called the null space of M. Because we're looking for orthogonal directions, we need to solve a set of equations that give us orthogonality. There's a set of linear equations that are equal to 0. So M times V naught is equal to 0. That's called the null space of M. That's just terminology. So we find the null space of M, and then this projection matrix that we need for the algorithm is just the product of those two vectors themselves. So it's V naught times V naught transpose gives us this PS here. So that's how we find the null space, and that's how we find this projection vector. So the linear algebra behind that, you can go back and read that section on orthogonal projections, but that's a summary of those few theorems that stack together to actually find these set of orthogonal projections for us. Once we have that, it's a few steps to just calculate this PS, and we can calculate these descent directions. And then around we go. So that's the algorithm. Here it is in MATLAB form. There's a lot of cleverness in this MATLAB code here. This is particularly useful to pull out just a couple of things. At various points, we need to find, we need to compare things with 0, right? So numerically, it's never a good idea to check whether something is equal to 0, because things are almost never equal to 0 because of floating point precision issues with computers. So often we'll compare with a tiny number. So we define a tiny number here and we compare quantities with that. So here's the other important thing to point out here is that to find the null space, to solve this system of equations with zeros on the right-hand side, in MATLAB, there's a nice command to do that, which is just the null command. So once we've formulated this special matrix M, to find its null space, we can just do that. We don't need to reinvent the wheel there or write new code to do that. MATLAB's got clever ways of finding those null spaces because it's a common thing. And then there's an algorithm that's built in there. Note that again, this issue of what happens when u is equal to 0, right? So we don't check that u is equal to 0. We check that u is smaller than some small number. But here, this terminates the algorithm at this point. We'll need to fix that up later. But for now, that's the gradient projection algorithm. That's it sort of formally. Keep in mind that this is the picture. This is what's really going on here. And if you keep this picture in mind, then you're going to understand the idea of this process of the gradient projection algorithm. So the next thing for us to do is to do a couple of examples to get this, to show how this works actually in practice. Then we'll talk about some of that theory and what we do when we can't find these feasible descent directions. And then we'll be able to build up the full gradient projection algorithm. But that's the flavor of it. And if you understand the picture, then that's how the thing works.